Here is an example. Okay. So, there are many inputs A, B, C, D, E, F and M and N are the outputs. Okay. So, assume that somebody has done the hard work of generating the list of faults. Sometimes it is useful to generate some random tests. Okay. In this example, there are 6 inputs. So, there are 2 to the power 6 possible test inputs. So, I will just generate randomly 1 0 1 1 0 1. Okay. Then we can try and see whether this, how good is this test vector, does it detect anything, right. So, let us go ahead and simulate a good circuit. So, 0 and 1 gives you a 1 here. This is an AND gate, 1 and 0 will give you a 0. This is an NOR gate, so this 1 will make this 0. This 0 will cause an AND gate to produce a 1, and this will get a 0 because both these inputs of this NAND are 0. Finally, this will give me a 0. So, this random test vector produced m equal to 0 and n equal to 0. Now, we have to see whether there is some fault which will cause m to become 1. Is there a fault? Which causes m to become 1 or n to become 1. See, this is a NOR gate. Currently, this has got a 1 here. So, the way this guy could become a 1 is if this is stuck at 0. Okay. So, stuck at 0 here will cause a, so that fault is caught. For this to become 0, if this becomes 0, that fault also will get caught. So, stuck at 0 on this wire, stuck at 0 on this wire, they are all caught. So, stuck at 0 on this and stuck at 0 on this will get caught. Now, can this become 0 because of one of these guys? Yes. This is a NAND gate. So, the output of this can change to 0 if this is stuck at 1. Okay. If this is stuck at 1, this will become 0. And how can this get stuck at 1? Maybe have I made a mistake? I think 1 0 I took it as, oh, this is a this is not an AND gate, this is an AND gate, this is okay. Okay. So, we can if this is stuck at 1 also it will get caught. So, red means stuck at 1, green means stuck at 0. So, if E is stuck at 1, then that will cause this to change to 1, and as a result this will change to 0. I think this should also be red, right. If this were to change to 1, this will also change to 1, and as a result this will change to 0. Okay. So, this particular vector can send okay, 1 0 1 1 0 1, okay. This vector catches E stuck at 1 and this wire stuck at 1, okay. And it also catches this wire stuck at 0 and this wire stuck at 0. Okay. We would have eliminated this. See, we are not interested, we are only interested in the faults at the primary inputs and the fan out branches. So, even though it catches this, it is not of importance to me. Okay. We are interested in this guy. Okay. Let me call this wire E1, E2, F1, F2. So, this is F1 and F2. So, F1 0 will be caught at M. So, whether E is stuck at 1 or F1 is stuck at 0, M will change to 1. What about N? When will N change? Currently, it is set to 0, a good circuit will produce a 0, and what conditions will the output N change to 1? Okay. That will happen if this has a stuck at 0 fault. Okay. So, if this has a stuck at 0 fault, this will change to 1, and if this has a stuck at 0 fault, it will change to 1. And we have already argued what can change this guy to 0. Okay. We have already finished our argument. So, there is only one extra fault, that is F2 stuck at 0. Okay. 1 0 1 1 0 1 catches F2 stuck at 0 at N. Okay. It also catches stuck at 1 fault here. It also catches a stuck at 1 fault here, but we have already talked about that. So, there are only 3 faults that this particular random pattern will catch. Okay. So, a random fault, random test 101 101 catches E0, E1, F10, F20. I can take a different random test. Okay, maybe I will take all zeros or something like that, and then I will do a good circuit simulation and then argue, right. This process of taking a test vector and finding what faults it detects is called as fault simulation. Okay. So, we say we did a fault simulation of 10101 and we found that these are the faults that will cause the outputs to change. So, going back to our ATPG. So, I had this big circuit and it had we had identified all the faults. Okay. So, we had identified the fault list. After compaction, then we can pick some random vectors, Okay. Now, how many, that is a choice that the user can take, maybe 20 vectors, okay, 10 vectors, 30 vectors. Okay. So, we can check some random text vectors and then fault simulate these guys, fault simulate the random vectors. Each of these random vectors will catch a few faults. Okay, let us say altogether the random vectors catch, let us say, these faults. So, the faults in this set. Okay. So, now we can go and eliminate them. We can say f equal to f minus r. So, these are all already addressed. And by experience, people have realized that random vectors tend to catch quite a few faults. Okay. So, if you take some 20 or 30 or whatever number of random tests, okay, these random tests can eliminate quite a lot of faults. This FR may be quite large. So, they have tried to study this, that is this is the number of random vectors and this is the number of faults that they catch. Okay. So, it sort of increases and then tends to sort of level off. Okay. So, initially you will adding more vectors seems to increase the number of faults that are getting covered, right. But over a period of time, it becomes little leveled off. So, up to this point, it is worth adding random vectors. Beyond that, random vectors are not very useful. It will increase very slowly. Okay. So, this is the optimal number of vectors that we can start with. You understood, no? So, whether it is 20 or 30, it is difficult to say. Okay. It depends on the circuit. You can even experiment. You can start with 10 and then double the number and see whether that produces a significant number of additional faults getting covered, then double again, and at some point you will realize that it is not giving any extra value. So, that is when you maybe you can stop. So, finally, we are left with some test vectors. I am sorry, finally, we are left with some faults which cannot be detected by random tests. Okay. We are now left with faults that random vectors cannot easily test. Unlikely to catch. That means it is now a matter of luck. Okay. We have to work very hard. Too many random vectors may end up getting generated if you try to do it this way. Now, we go to what is called as targeted test generation. That means, we pick a fault from F and generate a test vector. So, let us call this fault maybe G, and generate a test vector T for the fault G. Then fault simulate T, and let us say T catches the faults, let us say some Ft. It may catch many faults. Now go and say F equal to F minus T. So, because now we have already caught these faults. So, we started with maybe a million faults, random vectors may eliminate half of them. Now, we are looking at one at a time. Each of these faults will tend to eliminate several faults. Okay. We need to repeat this. Okay. Check if the fault list is 0, the size of the fault list is 0. If it is not, then we have to go back. Okay. So, this is how test patterns are generated. So, in our previous example, we generated 101, 101 and that eliminated these guys. Okay. What is our original fault list? Our original fault list included A0, A1, B0, B1, C0, C1, D0, D1, E0, E1, F0, F1. Then we had F1 0, F1 1, F2 0, F2 1. I am sorry, we have forgot this guy. We also had let us call this G1 and G2. Okay. We can do a little bit of compaction further by eliminating, for example, B1 and C1, we can eliminate one of them, okay, and so on. It may help you a little bit. Okay. But now I took a random test vector and that eliminated E1, F10 and F20. So, F20 is gone, E1 is gone and F10 is gone. I can take another random vector, it may eliminate a few more. So, if I take 20 random vectors, I may have eliminated quite a few of these. After all the random testing has been completed, I may still be left with a few faults. So, I will take one of them, let us say A0, and then I will generate a test pattern using the method that we discussed earlier. We activate the fault and then we propagate the fault, right. So, that will give me a test vector for A0. Then we fault simulate that vector and see what other faults it might catch, and we may end up eliminating a few more. And then we check, have we caught all the faults that we wanted to? If not, go back. Okay. So, that is the overall procedure for test generation. This is the test generation process. For combinational circuits. Okay. Okay.